Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website, arifpat.me. The other way is to download all the notebook files from a course GitHub account, Arif PUCIT, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.20 of the 6th module, Machine Learning, for the course titled Tools and Techniques for Data Science. So far, we have explored almost all the phases of a machine learning life cycle, starting from data acquisition to model deployment. However, we have only explored linear regression and its variants to predict a continuous output. Today we are going to switch gear and talk about classification algorithms. And you all know that unlike regression, where we predict a continuous number, in classification we predict a category. Classification models include linear models like logistic regression, which we are going to study today, and non-linear models like k-nearest neighbors and kernel support vector machines, which we will study in the later part of this course. So let's move on to the agenda for today's session. Well, we will start with an abstract overview of logistic regression, its types, its assumptions, and a brief discussion on why it is called logistic regression, whereas it is a classification algorithm. Then I will discuss the architecture of a single layer perceptron, which is a basic computational unit of a neural network that is designed to perform binary classification of input vectors. Over here I will of course use the Desmos calculator to tell you as to how we can find the weights of the classification lines or the decision boundary. And once we are equipped with all the theoretical background, we will use the logic of single layer perceptron with step function to perform the classification task. We will then compare the results with the Scikit-Learn's logistic regression model. And finally, we will discuss the limitation of using step function, and instead we will use the Sigmoid function and a slightly improved algorithm which will give us results quite close to Scikit-Learn's results. Well, this is going to be a very informative session, so let's move ahead and start playing. My dear students, let me give you an abstract overview and a basic intuition behind logistic regression before we jump into its math and Python implementation. So let me spend a few minutes to set the stage right by answering the what, why, and the how questions. Well, a logistic regression is a statistical model that allows us to predict a categorical label based on historical feature data by predicting the probability of an outcome, event, or observation. Let me describe a logistic regression model using this image. Suppose given a set of 3 input features x1, x2, and x3, we want to predict whether the penguin is happy or sad. And suppose these x1, x2, x3 are the 3 input features, which can be, for example, x1 can be the availability of fish to eat for this penguin, x2 is the temperature or maybe the weather, and x3 is the fear of maybe the snow bear. Now, these features may have a positive or negative impact on a penguin to be happy or sad. Moreover, these three events might not contribute equally towards these two possible outcomes. So, we need to find out the proportional contribution of all the three events which make these penguins happy. This proportional contribution is called weights that we will be representing interchangeably with a W or maybe theta symbol as shown over here. Well, in logistic regression, we multiply the feature values with their corresponding weights and sum them up to arrive at a value which will determine whether that specific penguin having these feature values is happy or sad. My dear friends, in a similar fashion, to classify a picture as a cat or dog or maybe a circle or a triangle, logistic regression will learn the weights of different features and then those weights will work together to assign a probability to that picture being cat or dog. I think I have given you an abstract overview of the working of logistic regression. So let's move ahead. Okay. Now, my dear friends, based on the output label, logistic regression can be divided into these three categories: binomial, multinomial, and ordinal. We use a binomial logistic regression when the output response or dependent variable has only two possible outcomes, a 0 and a 1. For example, classifying an email as ham or spam, classifying an online transaction as fraudulent or not, classifying a tumor as malignant or benign, and so on. My dear students, when the output label has three or more categories without ordering, we use multinomial logistic regression. For example, classifying sentiments, emotions, and parts of speech. Multinomial logistic regression works by mapping outcome values to a range of values between 0 and 1. And finally, when the output label has three or more categories with some intrinsic order, we use ordinal logistic regression. And examples of ordinal responses include maybe airline passenger class, student letter grades from maybe A to F, ranking a customer service as poor, fair, good, or maybe excellent. I hope this is clear. Okay, my dear students, one of the main requirement of logistic regression is that the data has to be linearly separable. Let me describe this concept with the help of this image. These three graphs show geometric representation of three different data sets having two input or predictor variables, x0 along the horizontal axis and x1 along the vertical axis. There is no output that is mentioned, rather the two classes to which these data points belong is represented by blue and red color. In linear regression, we are used to of keeping the output or dependent variable along the y-axis and input feature along the x-axis. But in these graphs along both the axes, we have input features or predictor variables. The class to which the data points belong is represented by colors or maybe by symbols like circles or crosses. Well, in all these three graphs, the data points represented by blue color belong to, say, class 0, while the data points represented by red color belong to class 1. I think the geometric representation of these graphs is clear. Now let me try describing as to what do we mean by linearly separable data. Well, linearly separable data is data that if graphed in two dimensions can be separated by a straight line. The dataset shown in the left graph is linearly separable because there exists a line, rather many lines, in this case from lower left to upper right corner, that separates the blue and the red classes. If the data is linearly separable or almost linearly separable, we can use logistic regression to predict or classify as to which class a specific data point belongs to. On the contrary, the middle and this right graph represent two data sets that are not linearly separable. The data in the middle needs two straight lines, while the data on the right needs a curvy line. And just as a side note, remember a logistic regression, support vector machine, and naive Bayes are linear classifier, while k nearest neighbor, Decision tree, and random forest are non-linear classifiers. My dear students, before moving ahead, let me tell you one more thing, and that is, in case of two input features, there will be a line that will be separating the data points belonging to these two classes. In case of three or more input features, it will be a plane or hyperplane. I hope this makes sense. Okay. I think this is the right time to talk about assumptions for logistic regression. And we all know and have discussed in detail the four assumptions for linear regression, which are linearity, independence, homoscedasticity, and normality. In contrast, logistic regression does not require a linear relationship between input features and output label, does not require homoscedasticity, that is the residuals to have constant variance, does not require normality, that is residuals to be normally distributed. However, logistic regression do require independence among the input feature, this A point. It also assumes that the response variables can take two possible outcomes. Thirdly, it assumes that the observation in the dataset are independent of each other, that is, should not come from a repeated measurement of the same individual. The sample size should be of reasonable size. Extreme outliers, they highly affect the output of logistic regression, so it is assumed that there are no extreme outliers in the dataset. The sixth and the final assumption is feature variables are linearly related to log odds. Well, don't worry, my dear students, how to check these assumptions and what to do if any of these assumptions is not met will be discussed in the due course of this and upcoming lectures on logistic regression, inshallah. Okay, so before jumping into the math of logistic regression, let me quickly give you a comparison between linear and logistic regression and answer the question as to how we can do classification using regression. So both linear and logistic regression are supervised machine learning algorithms, and both models are parametric as they use linear equations for the prediction. Although named as logistic regression, but the algorithm is used to handle classification problems. Well, linear regression provides a continuous output, while logistic regression provides a discrete output. This is the second difference. The loss function in linear regression is sum of scared errors, while the loss function in logistic regression is maximum likelihood estimation. And soon I will be describing this in detail. Okay, now the question is, can we use regression for classification? Let me describe this with the help of these graphs. Consider this top left scatter plot representing some data points having height and weight of people. The height is the input feature or independent variable, and weight is the output feature, rather output label or dependent variable. And we need to predict the weight of a person given his or her height. So this is a simple linear regression problem where we draw the best fit line as shown in this graph. We have done this in all our previous sessions. Now consider this top right graph representing some data points having height, weight and obesity of people. In this case, height and weight are the two input features, while obesity is the output label having two discrete values. Obese mapped to a value of 1 and not obese mapped to a value of 0. So this is a classification problem having two input features. So we need to draw a line. Suppose somehow we draw this line which is shown over here and decide a threshold value, say 0.5, and note that all the points above 0.5 can be considered as obese, while all the points below 0.5 can be considered as not obese. My dear students, if you closely observe this graph, you will notice that this central area of the line is not of much usage. Moreover, if there exists an outlier somewhere, suppose over here where my mouse is hovering in our data set, at a very, suppose a very obese person, a red dot over here, the slope of the line will be reduced, and this threshold of 0.5 in that case might not work. So this linear line is highly susceptible to outliers, and to handle this we preferably use a step function as shown in this left bottom graph. Well, the real output value of obesity is given as input to this step function. The step function compares the obesity value with a threshold value, and if it is greater, outputs 1, and if it is less, outputs 0. So in simple words, this step function maps a real value to a binary value of either 1 or 0. My dear students, the limitation of this step function is that it cannot be used for multi-class classification. And to handle this limitation, we move on to another function called Sigmoid, which is actually used in logistic regression and is also called the logistic activation function. Its graphical representation is like the shape of an English alphabet S. Well, the sigmoid function also takes a real value as input and maps it to values between 0 and 1, not discrete output, but this time it is values between 0 and 1, which can be interpreted as the probabilities. Since the probability of anything exists only between the range of 0 and 1, so this sigmoid function gives us the probability of a data point belonging to a class. Okay, so far so good. My dear students, I think we are now ready to dive a bit deep in the logistic regression algorithm. Let me give you an intuition of solving logistic regression using a single layer perceptron. Perceptron is the first thing that you will be taught in your deep learning course. In simple words, a perceptron is the basic computational unit of a neural network. that is designed to perform binary classification of input vectors. Let me describe the working of a perceptron using this image. The input values or features are fed into the perceptron. Each input feature has an associated weight which determines the contribution of that input feature in the final output. And over here, this bias is a constant term that allows the perceptron to adjust the decision boundary. The summation unit takes the dot product of the two vectors, input and weights, and sum them up to get a real valued output. And this real valued output is passed through an activation function, which can be a binary step function, a sigmoid function, a hyperbolic tan function, a ReLU, a leaky LU, or softmax function. There are many activation functions which we can use over here. But over here right now, I've shown the binary step function which checks if this real valued output is greater than or equal to the threshold of 0, it will output a value of 1, else 0. My dear students, now a $100 question that might be coming to your mind is how logistic regression learns these weights. Actually, logistic regression use gradient descent algorithm to find the optimal weights for a given dataset by minimizing the error between the predicted probabilities and the true class labels during the training process. And this I will do inshallah in our next session. However, today I will use a comparatively simpler algorithm to learn all these weights. And that is using the Perceptron technique. Anyways, let me describe this geometrically first. So, before I tell you the algorithm actually, let me graphically show you a decision boundary in a small dataset of, let's say, 8 observations. Consider this scatter plot that shows the height and weight of 8 persons, which are the two input features. Just ignore the units over here along the horizontal and the vertical axis for this height and weight respectively. Also assume that these green stars belong to class say obese, while these blue circles represent the data points that belong to another class say not obese. And you all know that the decision boundary in logistic regression is a line or curve that separates the input space into two regions, one for each class. For, of course, two input features, this decision boundary is graphically represented by a line, while for three input features, it will be a plane, and for higher dimensions, it will be a hyperplane. Anyways, for easy visualization, I will restrict myself to two input features as shown over here. My dear students, one more thing you need to keep in mind is that in case of a linear regression, we considered the line equation as y is equal to mx plus c. On the contrary, in case of logistic regression, we consider the equation of the form as shown over here, where we multiply the weights with the feature values and sum them up. And this W0 is actually the bias. And this decision boundary shown in red color over here is represented by this equation, that is 3x1 plus 4x2 plus 2 equals 0. My dear students, there can be many different lines that can separate these data points into two regions. I have just shown one. Okay. One more point. All the input space above this red line satisfies this inequality, that is 3x1 plus 4x2 plus 2 is greater than 0, which I am calling the positive region. And all the input space below this red line satisfies this inequality. 3x1 plus 4x2 plus 2 is less than 0, which I am calling the negative region. Well, you can always verify this using the online calculator at desmos.com. Okay, for a crystal clear understanding, let me do that as well and open a new browser tab and write down desmos.com/calculator. Let me just write down the same equation which says 3x plus, let's suppose 4y plus 2 equals 0. So this is the line that I've just shown to you. Let me show you the regions. Let me say now 3x plus 4y plus 2 is greater than 0. So this is the positive region now. If you closely see, this is the positive region of this equation. And if I say, let's suppose 3x plus 4y plus 3x plus 4y plus 2 is less than 0. So this is the negative region that belongs to another class. Now let's see, given a data point, how can we determine if this point is in the positive region or it is in the negative region? Suppose this is a line. If a point is, let's suppose 2, 2, so it appears that this is in the positive region by seeing it graphically, but how we can do that mathematically? Well, it's simple. You use this point 2, 2, you plug in x is equal to 2 and y is equal to 2 in this equation. 3 times 2 plus 4 times 2 plus 2 comes out to be 16, which is of course greater than 0. And that is, it satisfies this inequality, and this point 2, 2 falls in this positive region. Similarly, let's consider this point minus 2, where my mouse is hovering. Visually, it appears that it is in the negative region. And if you just plug in x is equal to minus 2 and y is equal to minus 2 in this equation, it will result in minus 12, which is of course less than 0. So it satisfies this inequality, and therefore it lies in the negative region. Let me fall back to the notebook. Do play around with this about any confusion if you have. I hope this entire image is clear to you. Now let me describe the algorithm using which we can find the weights W1 and W2 corresponding to these two input features and the bias W0. And of course it is assumed that we have a reasonable number of observations or data points. Let me now describe the algorithm at an abstract level. We initialize the weights or coefficients with some random values. We then enter in a loop which runs either a fixed number of times or maybe till convergence. And in each iteration of the loop, we select a random point. If it is correctly classified, that is a positive point in the positive region, or negative point in the negative region, we leave it. And if it is a misclassified point, we move the line towards the point. So this is the algorithm. Now a $100 question is how to identify a misclassified point. Consider this image now. As per this solid red line, these 4 1, 2, 3, 4. These 4 blue points are negative as per their labels and are in the negative region. So these 4 blue circles are correctly classified. Similarly, these 4 green points represented by these green stars are positive as per their labels, and since they are in the positive region, so they are also correctly classified. Excuse me. Now consider this blue point, which is negative as per the label but is there in the positive region. This is the condition that we can use to identify it, which says if X actually belongs to negative region as per its label and its a dot product, that is Wx, and the sum of it is greater than equal to 0, then it is misclassified. So this is the condition using which we can identify a misclassified point. Now consider this a green point, this green star where my mouse is hovering, which is positive as per the associated ground label, but is there in the negative region as per this solid red line. And this is the condition that we can use to identify it, which says if X actually belongs to P, that is a positive region, and the sum of its dot product of W and X is less than 0, then it is misclassified. My students, I hope now you know as to how we can identify a misclassified point. The next $100 question is how to move this solid red line so that the point falls in the correct class or region. As a rule of thumb, remember, if a misclassified point is in the positive region, you subtract. And if a misclassified point is in the negative region, you add. Consider this misclassified point, this blue circle. As it is on the positive side, so we have subtracted a small amount of values from the old weights to update these weights. And this symbol eta is actually the learning rate. That is, instead of subtracting the feature vector as such, we multiply the feature vector with the learning rate and then subtract. My dear students, remember in machine learning we never apply large transformations. Instead we take a small number called learning rate, like 0.01 or 0.1 maybe, multiply it with feature vector and then do the subtraction. Similarly now, consider this misclassified green star, this green point. As it is on the negative side of this solid red line, so we have done the addition as shown over here in this equation. Well, these two transformations will finally transform the solid red line to this dotted red line. And now all the points you see are correctly classified. All the blue points are on this side of this dotted red line. All the green stars are on this side of this dotted red line. I hope I have made the point clear. If not, do revise this part of the video, pause it for a while, think, and then move ahead. So this is the algorithm. In line 1, I have actually initialized the number of iterations or epochs to 100 and learning rate to 0.01. In each iteration of the loop, I pick up a random point, which can be from the positive side as well as from the negative region. If it is a negative point, in the positive region, I subtract learning rate times feature vector from old weight. If it is a positive point in the negative region, I add. My dear students, do note that in each iteration, we update the weights only if the randomly selected point is misclassified. Otherwise, we are making no change to the weight vector. Well, a more elegant way of writing this algorithm without using the two if conditions is shown over here. Here yi is the actual label and this yi hat is the prediction. If the data point is correctly classified, then yi minus yi hat will be 0. 1 minus 1 will be 0. 0 minus 0 will be 0. So no update will occur because this second term will become 0. If yi is 1 and yi hat is 0, that means a positive point in negative region. And 1 minus 0 is 1, so addition will be done. On the contrary, if yi is 0 and yi hat is 1, that means a negative point in positive region and 0 minus 1 equals minus 1. So a subtraction will be done. Beauty. Beautiful. My dear students, I think now we are ready and very much clear about the theoretical aspects of logistic regression algorithm. Given a data set, we start with some random weights, draw a line, enter in a loop, select a data point at random. If it is correctly classified, we do nothing. If it is wrongly classified, we update the weights using this formula. Good. And to calculate this y hat in this algorithm, we calculate the sum of the dot products of w and x vectors and pass this real value to this step function, which returns us either 1 or 0. Let us now make our hands dirty to practically implement this in Python. So let us first generate a synthetic random dataset using make underscore classification method of datasets module of Scikit-Learn. The parameters n underscore samples is equal to 100. This means that we want 100 observations or data points. N underscore features is equal to 2 means I just want 2 input features per sample. N underscore classes is equal to 2 means I want to do binary classification. Moreover, I have specified number of clusters per class as 1, separation among the classes is 20, and random state is 41 for reproducibility. Do go through the help page to check out the details about these parameters. Let me just execute this code cell. It has returned me 2 arrays x and y. X contains the 2 input features, 100 data points, while this y this contains the ground labels 1 or 0 for these 100 data points. Let me show you the contents, just the initial 5 rows of x and the entire y. So these first 3 observations belong to class 1. The label is 1. This 4th observation belongs to class 0. This 5th observation belongs to class 1, and so on. Okay, let's now visualize the dataset. For that, I've used the scatter plot method. I'm just keeping the 0th column of x along the horizontal axis and the first column of x along the vertical axis. Then I'm mentioning the color and size of the points. Let's just execute. Great. Seems to be quite a balanced dataset having almost equal number of samples belonging to both the classes, represented by blue and green color. Okay, let me now describe this actual piece of code which I have written inside a function named Perceptron. And we are actually going to update the weights using this formula mentioned over here. This Perceptron function is passed the input feature X and the ground label Y. This first line is using the insert method of NumPy to insert an additional column at index 0, all having a value of 1. So we have, after this line execute, this X will have 3 columns. The first column will be of all ones and the next 2 columns will contain the feature values. Okay, I think this makes sense to you now. Okay. Then I am initializing the learning rate to 0.1 and number of epochs to 1000, which are the hyperparameters. Do play around with these values to see their impact on the final result later on. Inside the loop, I am selecting a point at random, that is an index from 0 to 99, and keeping that index in J. Then I am using the step function to calculate the value of y hat, which is equal to the sum of the dot product of feature vectors and weight vector. And this is the step function. Over here I have defined it. I hope this makes sense. Anyway, after calculating this y hat, this line is actually updating the weights using this equation which is mentioned up over here. And finally, when the loop ends, this function is going to return the bias which is there at the 0th index of the weights vector, and the weights for all the input features. In this case there are just 2. Let me just execute this Perceptron function and this step function as well. Now in this code cell I am just calling this Perceptron function and passing it the input feature X and output label Y. It do all the training and finally return the bias and the weights. Let me just execute it. Great. So the bias is 1.3, weight of first input feature is 1.01, 1.05, and W2 is 0.22. Now let us use these weights to plot the line that separate out the points into 2 classes. To plot a line we need slope and y-intercept. Well, the slope will be equal to minus W1 over W2, and y-intercept will be equal to minus W0 over W1. So we have got the slope and the y-intercept from these weights. These 2 lines are actually generating the x and the y points to draw the line. And then over here we are just plotting the line and drawing the data points using the plot and the scatter method respectively. Let's just execute. Great. My dear students, this is the line that we have drawn that separates the 2 classes using the single layer perceptron and the step function. Seems reasonably good. Okay, now I think it is time that we should use Scikit-Learn's logistic regression model and compare results of our algorithm with logistic regression. Let me just walk you through with this sample piece of code. Let me just execute this cell. So we have created an instance of the logistic regression model. I have called the fit method on it and passed it the x and y. Now we have the trained model. Let's display the model's intercept and coefficients. The weight seems a bit different as compared to the ones we computed above using single layer perceptron, of course. But let's just visualize by plotting the line. And in this code cell, I am plotting both the lines. Note, I am plotting both the lines. The first plot method is plotting the line that was the result of single layer perceptron in red color, while this second plot method is plotting the line that is the result of Scikit-Learn's logistic regression model. Let me just execute. Great. These lines are quite different. Well, this black line is the result of Scikit-Learn's logistic regression model, which seems a bit better as it is having almost equal margins from both the classes. On the contrary, this red line, which is the result of single layer perceptron, is working on the training data but will fail on test or unseen data. So that means logistic regression is using some other algorithm, maybe. Let's see how we can improve our algorithm. Now, first try to find out the limitation in this algorithm. If you look closely to this equation over here, which we are using to update the weights, you will notice that we are only updating the weights of misclassified points. For correctly classified points, that is the points which are on the correct side of the line, this yi minus yi hat will be 0. So this second component will become 0. Hence this w new will be equal to w old. Moreover, this algorithm will work only till the time all the data points are on the correct side of the line. As soon as it is done, no matter how many more iterations we do, the weights will not be updated. Let me move up and show you the graph again. You can notice this red line. As soon as the last misclassified point is adjusted, the line stops moving. So now the question is how to overcome this limitation. So in this algorithm, we are only adjusting the line with respect to the misclassified point. We need to adjust the line with respect to the correctly classified point as well. Let's say that a misclassified point pulls the line towards itself, while a correctly classified point pushes the line away from it. Moreover, in case of a misclassified point, if the point is close to the line, it will pull the line with smaller magnitude. If the point is far from the line, it should pull the line with greater magnitude. On the contrary, in case of a correctly classified point, if the point is close to the line, it will push the line with greater magnitude. If the point is far from the line, it will push the line with smaller magnitude. My dear students, once again, please pause the video and visualize the logic behind what all I have said just now before you move any further. Okay, now the next natural question that will come to your mind is how we can implement this new logic. Once again, note this equation, which is updating the weights. The new model coefficients or weights is equal to old weights plus learning rate times y minus y hat multiplied by feature vector x. The update will occur only when y and y hat are different. When both are 0 or when both are 1, the weights will not change. If you recall, this was implemented using this step function. If the sum of the dot product of w and x is greater than or equal to 0, the step function outputs 1. And if this real valued output is less than 0, the step function places a 0 in this y hat. So this y hat can be either 0 or 1. I want to make a change in this model such that the output is not discrete. The solution is simple. We just replace this step function with a sigmoid function. Well, my dear students, this is what I have done. A sigmoid function is the most famous activation function in machine learning and deep learning. Graphically, it is represented by an S-shaped curve, and mathematically it is equal to 1 over 1 plus e raised to the power minus z, where this is the value of z. And e is the Euler's number, approximately 2.718, and is the base of the natural logarithms. Well, if z is very large positive number, if this is a very large positive number, sigmoid of z approaches to 1. If z is a very large negative number, sigmoid of z will approach to 0. And if z equals 0, sigmoid of z will be exactly 0.5. So by replacing the step function with sigmoid function, the value of y hat will not be discrete. Rather will be in the range of 0 and 1. And this will solve our problem. That is, now this yi minus yi hat will not be 0 even for the correctly classified points. Since the output y hat now range from 0 to 1, so we can interpret it as probability. Okay. Well, for crystal clear understanding, let me describe the working using these 4 data points. This green star, this blue circle, and this blue circle. Suppose the data points represented by these 2 green stars belong to positive class. So this green star number 3 is on the wrong side of the line and is misclassified. Similarly, suppose the data points represented by these 2 blue circles belong to negative class. So this blue circle number 4, this one, is on the wrong side of the line and is misclassified or wrongly classified. At any instant of time, this is the red line that represents the classification line. Now let me deal with all these 4 points one by one. Consider this point 1. Suppose it has a z value of 2, and when this z value is passed to sigmoid function, we get a prediction or y hat of 0.88. Now this y minus y hat becomes a positive 0.12. So this correctly classified point will push the line away, that is downwards. Similarly, this second point, point 2, this blue circle, is also correctly classified, having say a z value of -2 and y hat of 0.1. So this y minus y hat becomes negative 0.1, negative. So this point 2 will also push the line away, that is upwards. Now consider this point 3, which is wrongly classified, having a z value of let's say -0.2 and a sigmoid or y hat of 0.45. So y minus y hat becomes positive, that is positive 0.55. So this point 3 will pull the line towards itself, that is downward. And finally, this fourth point is also wrongly classified, having say a z value of 1 and a y hat of 0.73. So this y minus y hat becomes negative 0.73. So this 0.4 will pull the line towards itself, that is upwards. My dear students, please do this using paper pencil for better understanding. Pause the video, repeat this part, have a clear understanding, and only then move ahead. And I'm moving ahead and implementing this logic inside the Python code. Great. Well, this is exactly the same piece of code that we have used a few while ago while using the Perceptron logic using the step function. It is passed the two arguments x and y, input feature and the output label. The only change in this function is this line, where instead of passing the z value to the step function, now we are passing the z value to the sigmoid function. And this is the sigmoid function. So we have just replaced the step function with the sigmoid function. Let me just execute these two code cells. And now let me call the Perceptron function that uses sigmoid and print the bias and the weights. Great. So the training is done. This code cell now draws all the three classification lines with the data points. You can see I am drawing all the three lines. Let me just execute. Great. My dear friends, this red line is the one that uses Perceptron with step function. This brown line is the one that uses Perceptron with sigmoid function that we have done just now. And this black line is the one generated by the Scikit-Learn Logistic Regression model. The brown line is still not close to Scikit-Learn's solution. It has improved a bit. From this red line, this brown line is a bit improvement. Let me move up over here. Well, if you increase the number of epochs from 1000 to say 1 million, you will get, I think, a far better result. But of course, it will take quite a bit of time. Do try it at your own. And in the next lecture, we will see as how gradient descent algorithm will help us to compute the same result as Scikit-Learn in far less time. So that is all for today's session. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.